Welcome back, students, to my course, Fundamentals of ArcGIS. And from this video, we will start our modules 8, which will be dedicated to calculating slope, DEM, aspect, and isolines. And at first, I will introduce it to some theoretical concepts of these definitions. So let's start our lecture. At first, let me introduce to the digital elevation model in case if you didn't heard about it. A surface can be defined as a geographic phenomenon represented as a set of continuous data. For example, rainfall, temperature, ice thickness of a glacier, or organic matter content of a soil. A continually varying surface can be represented by isolines, and these contours can be effectively regarded as sets of closed and nested polygons. Also, contours are a very suitable presentation form of a continually varying surface. They are not particularly suitable for numerical analysis or modeling. So all the data formats were developed in order to be able to represent and to use effectively in spatial analysis where a continuous phenomenon is involved. A surface model is an approximation of a surface. Surface models are stored and displayed as rasters, datasets, or TINs, which is defined as triangular irregular networks in vector format. Because of a surface contains an infinite number of points, it is impossible to measure and record the value at every point. A surface model approximates a surface by taking a sample of the values at different points on the surface and interpolating the values between these points. A widely used surface model in GIS is a digital terrain model, DTM. This is a digital representation of the continuous variation of the topography over space. A well-known example of a DTM is the digital elevation model, DEM, a digital model of a topographic surface using information on elevation of the land surface. All the examples of the digital terrain models are models of slope or aspect. Note that these terrain models are derived from DEM. So these are the four images of the concepts we were talking about. On the top left corner, you can see the digital elevation model, a topographic model of a surface of a certain area. So green areas have a low elevation, and the orange and brown areas have high elevation beyond the Earth's surface and sea level. On the right top corner, you can see a slope map, a terrain steepness. So slope is measured in degrees. If digital elevation model is measured in meters, the slope measured in degrees, and slope model is always derived from the digital elevation model. So it shows the steepness of a surface in degrees from 0 degree to 90 degree. 0 degree is a flat terrain, and the 90 degree is a steep terrain. And in the bottom left corner, you can see a model of a triangular irregular network. So triangular irregular network also represents the topography of a surface, but if the digital elevation model is always a raster type of DTM, TIN is a vector model of DTM. And on the bottom right corner, you can see the slope, the aspect of the surface. You can see here the aspect. I will introduce you what the aspect means. So in this, in our image, aspect is divided into several classes: north, northeast, east, southeast, etc. So on the following slides, I will explain you what this classes does represent. So aspect a little bit differs from slope, but it also derived from the digital elevation model. So slope. The slope tool identifies the steepness at each cell of the raster surface. The lower the slope value, the flatter the terrain. The higher the slope value, the steeper the terrain. The output slope raster can be calculated in two types of units, degrees or percents. So this is how the slope is measured in from the basic course of the geometry. So rise and rise is a vertical axis and run is a horizontal axis, and the ratio of rise and tan is the tangents of a slope. It's where when we measure in degrees, while in percents it's rise and run. Percent of slope is ratio of rise and run is multiplied to 100. So the percent rise can be better understood if you consider it as the rise divided by the run multiplied by 100. Consider triangle B above. When the angle is 45 degrees, the rise is equal to the run and the percent rise is 100%. As the slope angle approached vertical 900 degrees, is as in triangle C above, the percent rise begins to approach infinity. The slope tool is most frequently run on elevation dataset, as the following image shows. The steeper slopes are shaded darker brown on the output slope raster. So the tool can also be used with other types of continuous data, such as population, to identify sharp changes in value. So mostly in ArcGIS for representing social and economic information, we use a vector information, but in case you want to use raster information, you can use also DTM, and also you can use in this case slope raster, slope raster in order to show the ratio between two indicators. Two methods of slope calculation. Two methods are available for slope computation. You can choose between performing planar or geodesic calculation with the method parameter. For the planar method, the slope is measured as the maximum rate of change in value from a cell to its immediate neighbors. The calculation is performed on a projected flat plane using a 2D Cartesian coordinate system. The slope value is calculated using the average maximum technique. With the geodetic method, the calculation will be performed in a 3D Cartesian coordinate system by considering the shape of Earth as an ellipsoid. So you can see in the right corner, top right image, how the geodetic slope is calculated. So longitudes and latitudes are used here, and the T is the target location of the pixel, for instance, and how the slope is calculated in this case. Both planar and geodesic computations are performed using a 3x3 cell neighborhood. For each neighborhood, if the processing center cell is no data, the output is also no data. The computation also requires at least 7 cells neighboring the processing cell have valid values. If there are fewer than 7 valid cells, the calculation will not be performed and the output that processing cell will be no data. The cell in the outermost rows and columns of the output raster will be no data. This is because along the boundary of the input dataset, those cells do not have enough valid neighbors. So aspect now. The aspect tool identifies the direction the downhill slope faces. The values of each cell in the output raster indicate the compass direction the surface faces at that location. It is measured clockwise in the degrees from 0 due north to 316, again due north, coming full cycle. Flat areas having no downslope direction are given a value of -1. So aspect is always derived from the digital elevation model, and it shows the direction the surface faces at that location, where 0 here, and from the image on the right you can see that 0 degrees indicated as north is the north class on the image is almost 0 degrees, from 0 to 22.5 degrees. the surface faces that location. So it represents the direction of the downhill slope, and flat areas have no downslope direction and a given value of -1. Aspect application, so where you can apply aspect dataset. Find all north-facing slopes on a mountain as part of a search for the best slopes for skyruns, for instance, right? So you're searching areas with the slopes facing north. Calculate the solar illumination for each location in a region as part of a study to determine the diversity of life at each site. So you're searching the area where which gets the most sun radiation during the sunrise on a certain area, mountain area. Find all southerly slopes in a mountainous regions to identify locations where the snow is likely to melt first as part of a study, to identify those residential locations likely to be hit by runoff first. So we can use this aspect during the flood assessment, during the hazard assessment, and landslide susceptibility, etc. Identify areas of flat land to find an area for a plane to land in an emergency, etc. So applications of surface analysis. In this case, surface analysis have many uses. Among the most important are the following. For hydrological analysis, at first, three-dimensional display of landforms of landscape design and planning. For planning routes of roads, locations of dams, etc. For statistical analysis and comparison of different kinds of terrain. For computing slope maps, aspect maps, and slope profiles that can be used to prepare shaded relief maps, assist geomorphological studies, or estimate erosion and runoff. Provide data for image simulation model of landscapes and landscape processes. So last one is isolines. Contours are lines also referred to as isolines that connect points of equal value such as elevation, temperature, precipitation, pollution, or atmospheric pressure. The distribution of the lines show how values change across the surface. Where there is a little change in the value, the lines are spaced farther apart. Where the values rise or fall rapidly, the polylines are closer together. Elevation contour lines are derived from a DEM. You can access the contour function in Arc Toolbox and in the Spatial Analysis toolbar. The latter is the most convenient for mapping contour lines. The contour function does not connect cell centers. It interpolates a line that represents the most likely location with the same height. Since the lines are smoothed, an idealistic representation of the surface is produced. You can also create an individual contour line by clicking the contour tool and then selecting a location in the view. The function traces the contour of the value that the chosen point represents. Hey guys, if you liked the video, please consider supporting the channel by purchasing online courses via my Udemy's profile, JS Lab. Here you can find multiple courses regarding JS remote sensing. The link to the profile is below.